Good afternoon, everyone. Today we're going to do an example where we look at a function f of x being 3x squared plus 18x plus 4, a regular old quadratic function, and we're going to look to find the inverse relation, f inverse of x. We're going to decide whether or not this inverse relation is in fact a function, looking at the vertical line test, and then we're going to look at a point on the original curve f of x and its image point on the inverse relation. Okay? Make that a bit clearer. So let's start by getting the inverse relation of f of x. And so to do that, we know we just swap the x and y's, right? So we plug in y's for x's and x's for y. And so what we get is x is equal to 3y squared plus 18y plus 4. And this looks like an awful mess to try to solve in this form, right? Because we have two terms with y and we're trying to isolate y. That's going to be a problem. And so what we can do is something we learned maybe a couple years back, is complete the square, right? So we'll have x is equal to, remember to complete the square, we factor the first two terms, and we can pull a 3 out of those, so we have 3 bracket y squared plus 6y plus 4. Keep going, y is equal to 3. Remember, we take half of the y coefficient, and so we have y plus 3 all squared. And now, we've just created a term out of thin air, right? To make our equation more convenient to work with, but we have to balance that out. Because y plus 3 all squared, when we expand it, would give us y squared plus 6y plus 9. And furthermore, the 9 that we just spontaneously created would get multiplied by the 3 that's hanging out front for 27. And so to balance that out, we have to subtract 27 to keep our equation balanced out. And now we can go ahead and finish off. X is equal to 3 bracket y plus 3 all squared minus 27 plus 4 means minus 23. And now that we have it in fully, let's say in transformational form, we can go ahead and solve for y, because you notice that there's only one term with the y, right? And so that allows us to isolate it. Now I'm just going to run through this. This is just algebra. So we'll have 3y plus 3 all squared. That's an awful looking 3 is equal to x plus 23. I just changed them sides because I'm so used to having the y's on the left side. Now we have y plus 3 all squared is equal to, let's divide both sides by 3. And so x plus 23 all over 3. Now we'll take the square root of both sides. Make a note of that, square root and square root. And when we take the square root, remember to take the positive and the negative version, right? And we have that y plus 3 is equal to positive or negative square root of x plus 23 all over 3. And then finally, we have y is equal to positive or negative square root of x plus 23 all over 3 minus 3. And so that becomes our inverse relationship, f inverse of x. And we can write it as f inverse of x is equal to positive or negative square root of x plus 23 all over 3 minus 3. Okay, I'm sorry that little bunch up there. A little crowded, but that's okay. So there's our f inverse relation. We can't call it a function yet because we don't know whether it passes the vertical line test, and you might get a hunch that it will not pass the vertical line test, because if we kind of graph this quickly even in our heads, the positive version of that square root term is going to give us a typical square root looking curve, right? Something like that. And then the negative version would give us simply the bottom side of that curve. And obviously, anywhere along this domain, you know, any x value has multiple y values, so we don't clear the vertical line test. And so because of that, clearly the inverse relationship between x and y is not a function. F inverse of x is a relation between x and y, but it is not a function. Now finally, if we do decide to graph both, even if f inverse of x is not a function, we can still graph it. It's still a valid relation between x and y. And so if the point negative 2, negative 20 is on f of x, where does this point get mapped to on f inverse of x? Well, we know that a mapping between f of x to f inverse of x simply sends a point xy on f of x over to, we simply swap x and y, right? That's how we started in the beginning. To actually get the inverse relation, we just swap the x and the y. And so the x and y becomes y comma x. And with that mapping rule in mind, we can apply it to this very specific point. This is a different color. And so with this relationship, with this mapping rule in mind, I should say, the point -2, -20 gets mapped to, we simply swap the x and y. And so on the inverse relation, that'll be at -20 and -2 for the image point. Okay? How this ends, I hope this creates a bit stronger connection between an original function and its inverse, the idea of whether or not a relation is a function, and kind of how to find image points for specific points on fx. Okay? If you have any comments, questions, suggestions, please do leave a note below, and thanks for watching.